In the lab today, we're going to be talking about how to make wireless communication possible to the Arduino. We're going to be using a PlayStation 3 controller, and as a result of the buttons pressed on the PlayStation 3 controller, we're also going to be adjusting the speeds and rotation of two different types of motors. We'll study both DC motors and stepper motors today. In order to do that, we're going to need to expand both the hardware and the software that we have in place for our system. So we're going to be installing a couple of expansion boards. Now, expansion boards on the Arduino are referred to as shields. So we're going to have, first of all, a shield that's going to enable a USB connection, a universal serial bus connection, just like the USB ports that you would have on your computer. And we're going to use that USB connection to connect a Bluetooth dongle. Now, the dongle is just a very small device. It's not a cable or anything. It's just a small thing that you plug into a USB port to allow Bluetooth connection. This is, for example, the exact same technology you would use for a wireless keyboard and mouse. That's exactly the technology we're using here. We're not going to be using it to communicate to a keyboard and mouse, though. We're going to be communicating with a PlayStation 3 controller. So that's the first piece of additional hardware that we're going to need to attach to the Arduino. We're also going to need to install 3 new libraries. And those 3 libraries are all zipped, and they're all stored on the Blackboard page for this lab. So we have USB Host Shield 2.0, Adafruit Motor Shield version 2, and then Excel Stepper Master. So these 3 libraries are all available on Blackboard, and you can download those. You can also get them from the original place where I got them as well. If you just Google that name, you can find those as well, and then place those in a location where you can access them, and then go to Sketch, Include Library, and Add Zip Library. Once you do that one time, you don't need to do it again, so that will make your life pretty easy. Remember that this is what we did when we had the LED matrix. We had to have the backpack library and the graphics library and the wire library, which we're also going to use again today as well. So next up, we're gonna do the first example. So if you go to File, Examples, USB Host Shield Library 2.0, then Bluetooth, then PS3 BT, and that's the PS3 Bluetooth example program. Before you upload that program, then go ahead and open that, but before you upload it, double check that you have connected the USB Host Shield and the Bluetooth dongle to the Arduino board. That's important that those are connected before you upload and execute this code. Now, there's a 11-step process here for pairing the PS3 controller to the Bluetooth dongle, and I will encourage you to follow that procedure. I've tried to write it as clearly as I possibly can. I also demonstrated it in the demonstration video. It can be a little bit frustrating, so if you run into trouble getting it to pair, ask for help. Try it a 3 times. If you've spent 2 or 3 minutes trying to get it connected and you're not having a lot of luck, then ask either your professor or your lab assistant, and they should be able to help you. Once you've paired the controller to the Bluetooth dongle, go ahead and open up a serial monitor and see what happens when you press different buttons or when you adjust the joysticks. Don't press that PS button again, because that will disconnect the controller and turn it off. If you do press the PS button, press it a second time, and then it will turn it back on and it'll reconnect. Couple of questions here just to verify that you did in fact get it to connect and that you're making the sort of progress that we're hoping to see. But that was interesting, but it's not as interesting as actually doing something. So in the next experiment, or in the next program, we're going to wirelessly control a couple of DC motors. Now, we've controlled DC motors in the past. We had a DC motor that we would turn on or turn off, but we could only turn it on in one direction. We could only make it go forward. Well, there's a good chance that you're going to want to use a version of this code to, say, program a robot. And robots are going to need to be able to go both forward and backward. So we're going to go one step further, and we're going to build what's called an H-bridge. Not build it, we're going to use it. An H-bridge involves 4 switches. Those switches will all be transistors for us. And if you close the top left and bottom right of those switches, then current flows through the top left switch, through the load from left to right, through the bottom right switch to ground. So current flows from left to right through the motor as shown here. If you close the top right and bottom left switch, then it flows from right to left, and if you flow current in the opposite direction of a motor, you will reverse the direction of the motor. So you can see here that in the second and third versions of this diagram, you can see that we do in fact have bidirectional control. But rather than using one transistor, now we have to use four transistors to be able to have this bidirectional control. So it's quite a bit more complicated circuit. You could easily spend the entire hour of lab today just building this circuit and maybe not get it to work even then. So So we're going to actually use another expansion board. We're going to use another shield. And the shield that we're going to be using is called the Adafruit. That's the name of the company. Motor Shield version 2.0. Version 2.0 because it's the second version. It's much better than the first version. You can see here that this has 4 motor ports. There's M1, M2, M3, and M4. And each one of those motor ports has 2 screw terminals. There's also a ground screw terminal that we're not going to use at all in this lab. But so motor 1 is these 2 screws, motor 2, motor 3 is these 2 screws, and then motor 4. We're going to be using this, first of all, to drive 2 DC motors. We could drive as many as 4, but it kind of isn't necessary to prove our point here. And then we're going to use it to drive 1 stepper motor on the left using 4 wires and 1 stepper motor on the right using 4 wires. And then there are also some other pins up here that we're going to be able to have access to. I will attach a small little breadboard area here so that if in your final design project, if you need to make some connections to any of those pins, you'll have that capability. But for today, we're really just going to be using this screw terminal and this screw terminal. And then when we look at the stepper motors, we'll be using the power bus screw terminal as well. So one other thing to mention is that a few of the wires on the motor driver shield are bent up, and that's digital pins 9, 10, 11, 12, 9, 10, 11, 12, and 13. Because those pins, I discovered that they were interfering with the operation of the USB port, and so I just bent them up so that it wouldn't make the connection. And so therefore, now they don't interfere with each other, and we can have USB connection and motor driver at the same time. So your first task is to connect 2 DC motors to M1 and M2. I would encourage you to plug them in so that the 2 red wires are toward the middle. So the 2 red wires, for example, would be on this screw terminal here and this screw terminal here. And the 2 black wires would be on the 2 outer screw terminals, top and bottom. If you do that, then when you press the joystick forward, then it'll cause the motors to rotate clockwise. And when you push it backward, it'll cause them to rotate counterclockwise. So we can then have a little piece of code here. I just want to talk to you briefly about this code because there's a lot of stuff in here that's going to be completely beyond the scope of our course. There's a lot of includes of different libraries. These libraries are either built into the zip files that we just downloaded, or we've previously downloaded, say, wire.h. There's a lot of libraries that we're including here because we're really stretching the capability of the Arduino. We're using 2 expansion shields, a USB, a motor driver. We're using a Bluetooth. We're doing a lot, and so we've got a lot of libraries to include here. Don't change any of those lines of code. Really, seriously, you're going to be Lab 24A is going to be the heart of your final design project. Just please don't change any of these lines of code here. Similarly, I beg of you, don't change any of these lines of code here because this is going to you might need to add 2 more lines for motor 3 and motor 4 if you're going to use 4 different motors for your final project. But other than that, all of these lines of code are pretty fragile. I've tried reducing this complexity, and my experience has not been good. So I would encourage you to just keep these lines of code the way they are. And then similarly, just seriously, don't mess with setup. There is a lot of stuff going on here in setup. If you're going to use the serial monitor, be sure to adjust it to a 115/200 serial communication rate. Everything else that's in here, I believe, you should not have to change, which means that it's really only when you get down to loop that you're going to need to be making some changes. And by the way, there's parts of loop that you don't want to change. So USB.task is the thing. This is the line that will connect the PS3 controller to the Bluetooth dongle. This is going to check to see if there's been a connection, and if there is, it gives it a. This is going to. If it has been connected, this will. And you press the PS button. This is the part that disconnects it. If a new connection is established, then it will print that to the serial monitor, and it'll give you a little rumble. So it'll say this is the duration of the rumble and the strength of the rumble on the left and on the right. So this is not necessary. You could take that out if you want to, but it's kind of nice to be able to have a tactile feedback when the connection is made. It's just a very, very brief, but it's still a nice connection. Here's the heart of the code that you will actually be able to modify or extend. You'll see that here we say, well, this thing is PS3. So PS3 dot get analog hat. We want to know what is the Y value of the left hat. If it's less than 118, then I know that I have pulled it back toward myself a little bit. And so then I want to set the speed of motor number 1. And I'm going to set that speed by mapping the numbers 128 down to 0, up to 200. So in other words, 128 is dead solid center on the Y analog. And if it goes down to 0 as I pull further and further back, I want to increase the speed of the motor from 0 up to 200. So the further I pull it back, the faster the motor will go. Similarly, if I'm pushing it forward, then it's going to range between 128 and 255, and I want to map that onto 0 up to 200. So this map command is really nice. This gives us the ability to figure out what is the minimum and maximum of the original value, the minimum and maximum of the new value, and do the conversion automatically. You'll see that here we're going to cause the motor to run backward, here we're going to cause the motor to run forward, or if we're near the middle, so if we're not less than 118 or higher than 138, remembering that 128 is the center, so there's a dead zone between 118 and 138, we're just going to release the motor. We're not going to be trying to hold it in place or cause it to rotate a little bit. We're just going to simply turn it off. So when you upload this program and then connect the PS3 controller, you'll be able to control one of the two motors using the left hat. Then I want you to extend this code to basically just taking this block of the code right here, making a second copy of it, to then look at the right hat and figure out what should happen to the second DC motor. Once you do that, then go ahead and demonstrate that to the professor or to the lab assistant. Then we're going to talk about stepper motors. And stepper motors are going to give you a completely different sort of capability. With DC motors, you adjust the speed, but you have really no control over the actual angle of the DC motor. Well, and similarly with servo motors, you can control the location, the angle, but you don't have continuous rotation. Stepper motors give us the best of both worlds. Stepper motors basically have a series of leads coming out, and here I think we can make out that there are 4 leads in this. That means that this is a bipolar stepper motor. And a bipolar stepper motor, the 4 wires come in 2 pairs. And that's sort of illustrated over here in part C. Here you can see that there are 2 coils. There would actually be multiple copies of each of these 2 coils. But A1 and A2, or sometimes it's referred to as A and A prime, B and B prime, or B1 and B2, those form the 2 sides of each of the coils, and you can activate each of the coils by turning them on or turning them off. You can see that what happens is if I activate, say, the A coil, well, that's an electromagnet. It's going to create a magnetic field that's going to line up vertically, and the south pole of the rotor is going to be attracted to the north pole of the electromagnet, so that we're going to rotate just as a compass rotates in the Earth's magnetic field. If we then activate B, well, then the south pole is going to turn toward B. If we activate A prime, then the south pole will go toward A prime. And if we do it in the correct sequence, and that's all about sequence for stepper motors, if we do it in the correct sequence, we can cause the rotor to have continuous rotation. Here you can see that there are actually 3 different types of sequences. There's actually a 4th called interleaved, but we're not going to use interleaved. We have full step sequence, which is actually in our program, it's going to be referred to as double stepped. Here we have the half step sequence, which will be referred to as single stepped. And then over here, we don't actually do a digital step. We don't do a binary turning them on and off. We do it with analog values. If we're slowly increasing and decreasing the voltages on the 2 different coils following a sinusoidal, and that's going to be a microstep. So here we have, I think it's 8 microsteps per step for that figure, so that you can see that we would have very smooth rotation. Now for the full step sequence, the motor will go faster and it'll rotate with more power. For the half step sequence though, it'll be more precise. As you could guess, we're going to have twice as much precision because the steps are half as big. Happily for us, we don't need to worry about the details of any of these sequences because it's all built into the Adafruit Motor Shield library. That's one of the zip files that we downloaded, and we're including it at the top of our program. Remember that here these are now called double steps, single steps, and micro steps. And we can also specify forward or backward. So here you can see that I would have a stepper motor called My Stepper 1. I'm going to take 100 steps forward, and they're single steps. And the stepper motors that we're working with have 200 steps per revolution, so 100 steps would be a half revolution. Or I could take 50 steps backward using micro steps, and those 50 steps then would be a quarter revolution, because 200 steps would be a full revolution. Now we're going to use this library to drive 2 stepper motors. First, you need to attach the screw terminals to 8 short wires, and so those 8 short wires are going to plug into 2 stepper motors. And that'll be stepper motor M1 and M2 are going to drive the first stepper motor, My Stepper 1. M3 and M4 will drive the second motor, My Stepper 2. But these stepper motors draw more power than the Arduino is capable of providing to this shield, so we're going to need to attach some external power. Let me scroll back up to the photograph of the motor shield and just remind you that right here is the power connection. And although it's really hard to see it, this is a jumper. This is the input voltage jumper. You'll need to pull that out. You'll need to take it out and put it somewhere safe, because I want you to put it back on again when we're done. Pull it out and then plug a positive voltage. Notice the positive sign right here. Plug a positive voltage into this screw and a negative voltage into this screw, and set it to 6 volts. So now the external power supply is going to be providing the power for the motors, whereas the USB cable will still be providing the power for the microcontroller. And when you do that, then run this program, which is very similar to the previous one, except instead of my motor 1 and my motor 2, we have my stepper 1 and my stepper 2. We specify 200 steps per revolution, and that it's attached to port 1 or to port 2. Now, port 1 for stepper motors is M1 and M2. Port 2 for stepper motors is M3 and M4. And then down here, exactly the same block of code for setup, except my stepper 1 and my stepper 2 are different. Oh yeah, so we set the speed for each of them to 10 revolutions per minute, which means that it would take about 6 seconds to do 1 revolution. Down here, we still have the same block of code, USB task, what happens if you disconnect, what happens if you connect. And here's the only part, again, that's really relevant for our purposes. If you click the up button, I want you to take 200 steps forward in single mode. If you click the down button, take 200 steps backward in single mode. If you click the left button, take 5 steps backward in microstep. If you click the right button, take 5 steps forward in microstep. And if you didn't click any of those 4 buttons, then release stepper motor 1. Because if you don't release a stepper motor, then it will continue to hold in that place. And just as if you're holding your hand very, very tight for a long time, your hand would get tired. In the same way that the motor is consuming energy, and it's going to perhaps get very hot. And so just be careful that if you forget to release the stepper motor, you might find that the temperature is going to get to be quite hot. Now you need to extend this code so that it will use the 4 buttons on the right side of the controller, triangle, circle, cross, and square, to control stepper 2 in exactly the same way, so that you'll have a symmetric control of the 2 stepper motors, using up, down, left, right for the 1 stepper motor and triangle, circle, cross, and square for the other stepper motor. When that's working, please demonstrate it to your professor or your lab assistant, and then disconnect the external power supply leads, replace the black plastic jumper, and then remove all the wires from the 10 screw terminals where you screwed them in, and then you're good to go for the week.